So let us look at what is minimization of Boolean expressions. What is minimization of Boolean expressions? See, when we minimize the Boolean expression, that means we want to minimize the appearance of number of literals in that Boolean expression, as well as we want to minimize the number of sum of product terms or product of sum terms in that particular expression. For example, if we have an expression like this, a b c complement plus a b complement c plus a b c plus a complement b complement c plus a b complement c complement. Assume we have this particular Boolean expression. Now this expression can also be minimized. How can we minimize it? We have already done some of these type of questions in the previous cases. So let us try to minimize this particular Boolean expression. Take this term and this term. You can take AB as common. So inside we have C complement plus C plus, if you take, assume you are taking this term and this term, then you can take B complement C as common. So inside we will be having A plus A complement plus A B complement C complement. So this will be AB plus B complement C plus AB complement C complement. Now if you take these two expressions, assuming if you are taking these two expressions, then you can take B complement as common, so it will be AB plus B complement C plus A C complement, and you can distribute C, so it will be AB plus B complement C plus A dot C plus C complement, so it will be AB plus B complement into C plus A. Again, if you open it, this is AB plus B complement C plus B complement A. Again, if you take these two expressions, then you can take A as common, so it can be written as B plus B complement plus B complement C, so it will be A plus B complement C. Right. Now if you take the original expression, the expression where we reached, we are having this expression and it is actually A plus B complement C, and this is the original expression. Now in this particular expression, how many literals are there? What are the number of literals? How many literals are there? So how many literals are there? Every occurrence of a variable is a literal. So 1, 2 and 3. So there are exactly 3 literals. And how many min terms are there? You can say number of min terms. So number of min terms here are 2. This is the first min term and this is the second min term. But if you take the original expression, then in this expression, what are the number of literals? Every occurrence of a variable is a literal. So how many literals are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So there are 15 literals. And what are the number of min terms? So how many number of min terms are there? These are 1, 2, 3, 4, 5. So there are 5 min terms. Okay. Now when we try to minimize a Boolean expression, then if you minimize the Boolean expression, then minimization is done when we want to minimize some kind of cost criteria. And that cost criteria may be including a lot of things. See, whenever we have these kind of expressions, we want to implement this expression using a circuit. Right, and in those circuits we are going to use the logical gates. For example, we are going to use AND gate, OR gate, NOT gate and all these kind of gates. Now in this expression we are going to require less number of gates, but in this expression we are going to require more number of gates to implement this. Our aim is, when we are minimizing, our aim is not to change the logical or functional characteristics of this expression. That means not to change the expression shown by this particular expression, the properties shown by this particular expression into this, but to minimize these kind of operators or operations. Okay, so we don't want to change the logical value of this particular expression while minimizing. Okay, so this is the main idea behind minimization of any expression. So when we want to minimize an expression, that means we want to minimize or we want to reduce some kind of cost criteria, and that cost criteria may be containing different kinds of measurements. For example, here you can say if you want to minimize the cost criteria, we should say that there should be minimum number of appearance of litters. For example, here we have only 3 litters, but here we had 15 litters. So the cost criteria can be, we want to minimize the minimum number of appearance of litters, and then we want to have minimum number of litters in SOP or POS expression, provided that there is no other such expression with the same number of terms and fewer litters. For example, in this case, we don't have any other such expression which is having same number of litters, that means 3 litters, and same number of min terms, right? So this can be minimized to this, and this is a unique expression, right? And third one is an expression from which no terms or literal can be deleted without altering its logical value is called as irredundant or irreducible expression. That means if you take this particular expression, this is a plus b complement c. Now you cannot remove any literal from this, you cannot remove any midterm from this without changing the logical value of this particular function. Okay, so whenever saying that an expression is irredundant or irreducible, that means for example, for this particular expression, you cannot reduce, or there is no redundant variables in this. There are no redundant variables in this, or you can say there are no redundant literals in this. There are no redundant literals in this, right? Not variables, actually I should say literals. So for this particular expression, there are no redundant literals in this. Therefore, this particular expression will be called as irredundant expression. Irredundant expression. So why, right? So what is redundant? Redundant means there's something extra which is not required, which is kind of extra, right? So an irredundant expression is not necessarily minimal, nor the minimal expression is always unique. There can be more than one minimal expressions. For this, for example, for this particular expression, we can have more than one different minimal expressions with the same number of literals. For example, that will be having 3 literals and same number of min terms. There can be more than one irredundant expressions, right? Right. So we cannot say that this irredundant expression is always unique. Right, so they can be different irredundant or irreducible expressions. Okay, so now let us see how to minimize a Boolean expression. Sometimes when you combine different terms in a Boolean expression, for example, if within a function, if there are more than 3 or 4 Boolean variables are there. For example, let us say if we have a function like this, f of a comma b comma c comma d, then it is ab cd plus ab complement c plus abc complement d plus abc complement d complement plus a complement b c d plus a complement b complement c d, and so on. So if in a Boolean expression there are more number of these kinds of variables, then this kind of expression becomes very difficult to solve, right? So because if we have 4 variables, then we are going to have at maximum 16 min terms. So these expressions become very difficult to solve. Therefore, we introduced one more algebraic procedure to solve more complicated Boolean expressions. Then that procedure is called as K-map, right? So in this K-map is basically, it is going to provide a systematic method for combining and deriving the minimal expressions. Next, a K-map is a modified form of truth table in which arrangement of the combinations is particularly convenient for minimization. Right, so I'll tell you each and everything. First of all, let us read it. Third is, every n variable map consists of 2 raised to power n cells. Fourth, K-maps are going to use cyclic code as row and column headings. Fifth, 2 adjacent cells play a major role in simplification because they can be combined by means of this particular rule. Let me tell you a very simple example here. Assume you have 2 variables. The variables are a and b, and there is a function f. The possible combinations can be 0, 0, 0, 1, 1, 0, 1, 1. And for this function f, it can have values like this: 0, 0, 1, 1, 0, 0, 1, 1. Now these particular combinations, we are going to represent these particular combinations by means of a map. For example, there are two variables, then for these two variables there are 2 raised to power 2 different combinations are possible. If there are n variables, then there are 2 raised to power n different combinations are possible. Now I can say like this: for these two variables I can make a k-map like this. This is A and this is B. This is denoting 0, this is denoting 1. Now a particular cell like this particular cell is representing 0, 0, this is representing 0, 1, this is representing 1, 0, and this is representing 1, 1. For example, this particular cell is showing A complement B complement, this is showing A complement B, this is showing AB complement, and this is showing AB. This is showing AB. Okay. Now if you have a 3 variable function, for example, we have these 3 variables, they are A, B and C. For these 3 variables, how many combinations are possible? They are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. Okay, these many combinations are possible. Okay, now for example, for these 3 variables, the k-map is going to contain 8 cells like this. This is a k-map with 8 cells. There are total 8 cells. This is representing A, this is representing BC, A and BC. Now in case of k-maps, we are going to use cyclic codes. You will get to know why we are going to use cyclic codes. First of all, you should know what is a cyclic code. You should know what is a cyclic code. Cyclic code means whenever we are going to have some codes, then all the bits will be having at maximum one a change of at maximum 1 bit. That means what I mean to say is, if I write 0, 0, after 0, 0 we can have 0, 1, because there's maximum a change of only 1 bit. Change of only 1 bit. After this we can have 1, 1, because at maximum there's a change of only 1 bit. After this we can have 1, 0, because at maximum there's a change of only 1 bit. Again, if you take this bit and this bit, there's a change of only 1 bit. In case of cyclic codes, we have a change of at maximum 1 bits only. Even if you have a 3 variables, then we can arrange the 3 variables in such a way that we get a change of at maximum 1 bit. Okay, so in case of k-map, we have a change of 1 bit. For example, here also, like this is representing 0, 0, this is representing 0, 1, this is representing 1, 1, this is representing 1, 0, this is representing 0, and this is representing 1. Here also you can see, from here to here there is a change of 1 bit, from here to here there is a change of 1 bit, from here to here there is a change of 1 bit, here to here there is a change of 1 bit, here to here there is a change of 1 bit. In case of k-maps, with 2 adjacent cells, there is a change of at maximum 1 bit. If you take any 2 cells, like for example, this cell is denoting 0, 0, 0, this is 0, 0, 1, this is 0, 1, 1, this is 0, 1, 0, this is representing 1, 0, 0, it is representing 1, 0, 1, it is representing 1, 1, 1, it is representing 1, 1, 0. If you take any 2 adjacent cells, for example, if you take these 2 cells, then there is a change of only 1 bit. If you take these 2 cells, there is a change of only 1 bit. If you take these 2 cells, there is a change of only 1 bit, like 0 is changed to 1. If you take these 2 cells, there is a change of 1 bit. If you take these 2 cells, there is a change of 1 bit. If you take any 2 adjacent cells in row and column, there is a change of at maximum 1 bit. There is a change of at maximum 1 bit, right? So for example, if you take these 2 cells, you know there is a change of 1 bit. Only 1 bit is changed from here to here. But for these 2 cells, what these cells are representing, this cell is representing A complement B complement, plus this cell is representing A complement B. Again, if you take any 2 particular cells, for example, if you take these 2 cells, then this cell is representing AB and this cell is representing plus A B complement, plus A B complement. So whenever we have 1 in 2 particular cells, for example, here in these 2 cells we have 1. Then we can make a subcube like this for these particular cells. And how can we make a subcube? To make a subcube, you can clearly see here in this expression, you can take A as common, so it is B plus B complement, which is equal to A itself. So therefore here, if you combine two cells, then they can be combined by means of this particular rule. By means of this particular rule. So this particular rule plays an important role in combination of variables in a K-map. For example, even if you have a 3 variable K-map, then these two particular cells can be combined. Why they can be combined? Because they have a change of at a maximum 1 variable. For example, this cell is representing A, B complement, C complement, and this cell is representing A, B complement, C. You can clearly see this AB complement, this AB complement, the only change is C and C complement. So if you combine these two cells, combining means you can take AB complement as common, so it is C complement plus C, which is equal to A B complement. Okay, so one more way of checking this is if you are combining these two cells, you can see what are the variables which are not changing. That variable will remain the same, and the variables which are changing, they will be eliminated while we are combining the particular cells. Okay, so we can say the two cells plays a major role in simplification process. And why? Because they can be combined by this particular rule. And these two cells are arranged because of the cyclic codes, because cyclic codes helps to create a difference of at maximum 1 variable. So whenever we are combining two cells, that means you are adding two cells, and because they have a change of 1 variable, and you can minimize that particular 1 variable. Okay, so let us look at more details about K-map.